only the first part of 8.8 because it's a little bit of a longer lesson here. And so we want to make sure that we can, get kind of the gist of things first. And then once we kind of work with that, then we'll dive into kind of the more challenging problems out of 8.8. So not that these won't be. So we're going to take a look at what we call a power series. And so this is our definition. So we will have an infinite series. So we'll be working with a variable of x, and we'll be having an infinite series. And so this is something that we're familiar with, except for what will be different is that we now have this x kind of introduced into our infinite series. And that is what makes that become a power series. So for example, like prior to here, like we would have, something like n equals 1 to infinity, and we'll have like, say, 1/2 to the n. And so we would say this is a geometric series, right? Geometric infinite series. And so what we're going to do is kind of, instead of saying like maybe 1/2 to the n, we'll do something like x over 2 to the n. So still it would be geometric because we have n as our exponent, but now this would be a power series. And what we would be searching for is like, what could x equal in order for us to have, a converging series, right? So this is a variable termed infinite series, right? So we'll have an x in there as well. And then our goal is to try to figure out what does x need to be in order for this geometric series to converge, right? So x could be 1 because that would make the ratio less than 1/2. So x equals 1, perfectly fine. But what if x were, say, 5? Could x be 5? And that would be no, because then that's like an x in terms of like, blah, not good. Because then I would have 5 halves, which is a ratio greater than 1, so it would not converge. Okay, so like that's like kind of the gist of what we're looking at. And that's the difference between what we would call an infinite series versus a power series, right? So that power series is going to have that variable of x in there. So more generally, the series of the form up here, so instead of just x to the n, it will have x minus c to the n, is a power series that we say is centered at c. So this is, kind of tying together what we did in 8.1 through 8.6 and then 8.7. So it's going to be kind of merging those two ideas together. And so a power series in x can be viewed as a function of x. So that would be, so we would have a different way to write a function, right? So we were saying our function of x is equal to this infinite series with a variable term in it, hence a power series. And the domain of our function, and this piece is going to be important because we're going to reference this often, is the values of x in which the power series would converge, okay? So the domain of our function is going to be whatever I can let x equal in order to have a converging power series. So this is really important for you to go back and review that 8.2 through 8.6 and making sure you know what were those rules again for testing for convergence. And so finding our domain of a power series is what we're going to be mostly concerned with. And so keeping that idea in mind. So this is where 8.2 and 8.6 will come back into play, is in 8.8. And so, and every power series will converge at the very least at its center. And that will be because when we were looking in 8.7 to convert things like e to the x, right, into a polynomial, whatever that would look like. So say something that looks like this, I don't know. And it was centered here, then guaranteed at that center, you will have this polynomial approximation equal to that transcendental function at that center, because that is that point in common. So you will always have at least one value in the domain, and that will always be at least the center. Okay, so this is what we have to make sure that we are understanding. Okay, so there's going to be a lot going on here. So we have from above, right, we have this an and then x minus c to the n, and then n equals 0 to infinity. So I'm looking at this right here. And it's saying that C is my center. So where do we look to find my center? We look to see what are we subtracting from the X value, okay? So here it says to state where is your power series centered. So our center is going to be at 0. Why is that? Because if I look up here, I have X, right? So what am I subtracting from X? Well, nothing. So I can always use 0. All right, for this one right here, so I want to find the center of this one. And so I'm looking here to see where is my X term. What am I subtracting from X? I'm subtracting 1. So my center would be 1. So that is all that question is asking. So is recognition, right? So where do I look for the center? And so if I had asked for like, what's the domain of this, we wouldn't be able to answer that question yet, but we could certainly say, well, I know for sure 0 would be in the domain of part A and 1 would be in the domain of part B, right? So I know that at least. So that's the first piece. Can we look at the power series that's given and find the center? All right, so for example 2, we want to find 3 values of X for which the power series of example 1a would converge. So this is 1a. So I know this is a geometric power series. Because I'm looking at where n is, right? So n is in my exponent, and so that's the only place it is, right? So that will make this be a geometric power series. The other thing that I know is that as long as that radius is less than 1, then my series will converge, right? So if the radius is less than 1, the series would converge. So I'm going to just do kind of a couple of guessing checks, and just so you can kind of get the gist. So here is my series, right? N equals 1 to infinity. And so I have over 2 to the power of n. So I'm trying to figure out what are 3 values for x I can put into here so that I would have a ratio that is less than or equal to 1, right? Like that's what we're trying to do. So let me just throw in some numbers. So I'm going to just start with 1. What if that was equal to 1? So if x were equal to 1, then my ratio would be 1/2, which is less than 1, so it converges. So x equals 1 works. Well, what if x were equal to 2? What if x were equal to 2? Then I would have 2 over 2 to the n, right? So keeping in mind I'm replacing x here. And so then the absolute value of my ratio would be 1, which is not less than 1, right? So that's not true. So x equals 2 cannot be in my domain, right? So that was a failed attempt. So x equals 2 is out. And so what if we did, so 1 was fine, right? 2 was too big. So what if we let x equal, say, 1/2? What if it was 1/2? Well, then that would be 1/2 divided by 2. So my radius would be 1/4, right? So 1/2 divided by 2 is 1/4, which is less than 1. So that's perfect. And so I'll let you try to find a third one in there, but I know there's 2 of them, right? So 2 values of x that I came up with, 1 and 1/2. That would give me a ratio of less than 1, which would allow that geometric series to converge. Okay, so let's take a look at this next component. So this is specifically talking about that domain piece again, and the domain, remember, is when the power series will converge. So there's 3 situations that could occur. So one is that the only thing in the domain is the center, so it would only converge at its center. So then it would only converge at the center. So the domain would only have one value in it, and that would be C. The other situation is there is some number r out there greater than 0 that the series converges absolutely for. And so that would be the absolute value of x minus c has to be less than r, so that's where it would converge absolutely. Or it would diverge whenever the x minus c value was greater than r. And we'll talk about what that is. So that number r that we're referring to is what we call the radius of convergence. So that is what we call the radius of convergence. So if we're within the radius, we converge. If we're outside of the radius, we would diverge. And then the third situation is that the series converges absolutely for all values of x. So then the domain would be all real numbers. Like that's what this would be saying. And if it was all real numbers, then we would say that that radius is infinity. Okay, so let's explain this piece up here just a little bit better. So like this portion right here. So this is just on a number line. So I'm just going to number line here. So my center is at C. And we're saying that the absolute value of x minus c has to be less than r. So what that means is from the center that you're going out so far to get to r. And absolute value meaning you're going in both. Oops, let's cut my arrow a little short there. Okay, so I'm trying to go to there. And then c minus r. So this distance that I'm traveling, I'm within r units, right? And so that's what we're looking at. So my center C, so wherever I'm centered, right? And I have to be within, so less than within R. So I mean, I can go forward R units or back R units. Okay. And we'll look at like, how did we solve that algebraically from your, I guess that would be math 2 days, I think, or math 1 maybe even. Okay, so what are the three situations? It only has one value in the domain, right? And so that would be the center, so one value. It has a finite section that we're looking at, not a finite number of numbers, but a finite area that we're looking at from like, you know, -2 to 3, or it's all real numbers, okay? All right, so endpoint convergence. So this piece right here is going to be on the 8B notes, and then exclusivity and inclusivity will also be on the 8B notes. Okay. So when we find that range of values for the domain, that is what we call the interval of convergence. So that interval of convergence and radius of convergence, we'll use that language often. And so that would be abbreviated ROC, so like rate of change, radius of convergence. But oftentimes we'll just say capital R equals. And then your interval of convergence, we abbreviate that with IOC. Okay, so let's go ahead and take a look at a few examples here to help us try to make sense a little bit of what we just talked about. So we want to state what is our center, what is our radius, and then what is the interval of convergence, right? So we want to figure out all of that. So here we're looking at, they tell us ahead of time that our series converges absolutely for this equation here, x minus 3 is less than 5. So we're referencing from above that we have the absolute value of x minus c is less than r, right? So that is what we're referencing up here. So remember, c represents our center, and capital R represents our radius of convergence. And then hopefully you are taking note of the fact that this is x minus 3, x minus 3, okay? X plus 2, x plus 2. Okay, so what is my center then? So my center will be equal to 3 because that's what I'm subtracting from x. My radius of convergence will be 5 because there's a 5 right here, right? So x minus c is less than r. So then my interval of convergence, so I'm going to show you just a couple of ways to think about that, so we are centered at 3. So here is 3. And our radius is 5. So that means from our center of like a circle, I can go 5 units to the right. So 3 plus 5, so that will land me at 8. But I can also go 5 units to the left. So 3 minus 5, -2. So then my interval of convergence would be from -2 to 8. And then I don't know if it converges or diverges on the endpoints, -2 to 8 at this point, because we have not looked at endpoint convergence. We will do that on 8.8b. So for now, we're just going to say it converges from -2 to 8, and we'll use parentheses until we learn otherwise, okay? So that's one way to do it. So our center is at 3, and then we're adding 5, subtracting 5. Another way to do this, so this is just kind of drawing on your old days of math 1 or 2, whatever day that was when you learned that. So if you had this equation to solve, you had to solve it by saying x minus 3 is less than 5, right? And the negative version of that has to be less than 5 as well. And then you would add 3 to the other side. Here you would divide by -1, so switch the inequality, and then you would add 3. Add 3. And so you would say x has to be greater than -2 but less than 8, and then that would be another way to get that section, okay? All right, so let's go ahead and take a look at this one right here. So again, we're converging absolutely for this equation. So then I'm looking here. So my center, what am I subtracting from x? That would be -2. My radius of convergence, so I'm looking here, would be equal to 1. So then my interval of convergence, right? So I'm centered at -2. And then from my center, I have a radius of 1, so I have to stay within 1 unit. So meaning I'm going to go to the right one, so -2 plus 1. And then I can also go to the left one, so subtract 1, so -2 minus 1, -3. So my IOC would be between -3 and -1. So that means, so just to clarify, if the domain of the power series would be -3 to -1. Meaning if I choose any number between -3 and -1 and replace this x here, then this would turn into a series that we know from 8.2 through 8.6 that would converge. So if I look at A, I have the interval of convergence is -2 to 8. So if I choose any value here between -2 and 8 and substitute it into this equation here, or that series there, it would turn into a series that I know converges from 8.2 through 8.6. Okay? All right. And let's take a look here. So for this problem, again, we're doing the same thing again. So we're looking for the center, the radius of convergence, and the interval of convergence. So this one right here is a little bit more, we got to work a little harder because I didn't give you that inequality. So we have to find that inequality. So I'm going to rewrite this just a little bit so that 1/5 does not have an X or an N on it. So that means it can go to the front of the summation. And so because it's just a coefficient, I'm going to go ahead and do that. So the first thing I want to recognize is that this is geometric. And then how do I know this is geometric? Because the only place I have N is in the exponent. And I know from whatever chapter or whatever objective that was, is that I have a geometric series when the ratio, or I have a converging geometric series whenever the absolute value of that ratio is less than 1, right? So that's what I know. So when I'm looking at this, I know that my ratio is this portion right here, right? So that is my ratio, not my radius, but my ratio. And so when I'm looking for the interval of convergence or the radius of convergence, so on and so forth, is that I know that I need to turn something into this whole business of x minus c is less than r, right? Like that, like I have to convert things into that. And then this will give me the values in which the series converges, right? So this helps me find when the series will converge. Well, I know this portion right here, right? So if the ratio is less than 1, I know that I have a converging series. So that's what I'm going to do. So I'm going to take the ratio, which is 2x, put it into its absolute value form, and make the statement that it has to be less than 1 in order for the series to converge, right? So the geometric series converges when the absolute value of r is less than 1, right? And so that's what I'm doing right there. So now I have, the start of this equation now. So now I have the start of this equation. So I'm going to have to clean it up a little because it needs to look like that. So the first thing I want to do is I have to recognize that this is not like, AX, it's just X, right? So I can't have that 2 in front. So the first thing I'm going to do is I'm going to divide both sides by 2. And that's just to get it to look more like that other equation. And so then once I do that, I have the absolute value of X is less than 1/2. And so now it's of the right format. And so now I can make my statements about my center, my radius, and so on. So my center is going to be, what am I subtracting from X? And that would be 0. My radius of convergence is going to be right here, so 1/2. And so then my interval of convergence, so I'm centered at 0. And I can go forwards 1/2, and I can go back 1/2. So my interval of convergence would be -1/2 to 1/2. So now here, we actually can do endpoint convergence, okay? So I know that because the ratio has to be strictly less than 1, right? It's not equal to 1, right? There's no bar there. So if it's not equal to 1, then that means that I cannot have close brackets here, right? So I know that X cannot equal 1/2. It will diverge. I know X cannot equal -1/2 because it would diverge. So the original series, so let's take a look right here. So if we look at this right here, what I'm saying is if I were to choose any number between -1/2 and 1/2, I would get a series that converges. So let's just check and make sure that, we have that idea. So there's a 1/5 here, n equals 0 to infinity. So if I were to let X equal 1/2, so I'm going to replace X with 1/2. So I would have 2 times 1/2 to the power of n. So half of 2 is 1. So if I have 1 to the n, my ratio would be 1, which is equal to 1, right? And then that means we have a diverging geometric series, right? Or if I think of this would be 1 plus 1 plus 1, all of that times 1/5, which would add up to infinity. And then you can always just plug in a few other numbers if you want to verify, but I'm just showing you that, this is going to be parentheses, right, instead of brackets, and that's because if X were 1/2 or -1/2, I would get an absolute value of a ratio that was equal to 1, which would be diverging. Okay, so let's take a look at one more here. Okay, so again, I'm going to do a little regrouping here to kind of see what I have, because remember what we need to have is, well, first, let me say this, is I have a geometric. How do I know I have a geometric? Because all of the ends are in the power, right? All of the ends are in the power. So I know I have a geometric. And so then the next thing I need to do is I need to get some sort of rule, like X minus C is less than R, right? I need to look like that. And how I'm going to do that is, because it's geometric, I'm going to first find, well, what is that ratio? And I know when the ratio is less than 1, I have a converging series. Okay, so let's do a little bit of rewriting. So I'm going to do this. So all of these are to the n power. So that means I can put all of these bases as 1 and do a quantity to the power of n, right? So these are all to the power of n. So I just took all of the bases and rewrote it. And so then I know that the absolute value of the ratio, so here's my ratio, because that's what's being raised to the n power. So the absolute value of that needs to be less than 1 in order for the series to converge. So I'm getting close to this, right? I can't have a coefficient. So this -1/2 I can't have there. So the absolute value of -1/2 is just 1/2. So let's pull that out just to get that there. And then now I'm going to multiply both sides by 2. And then now I have it in this format, right? So now I'm in that x minus c is less than r format. So I can say, okay, what's my center? It's what I'm subtracting from x. What is my radius? My radius is 2. And then now let's find my interval of convergence. So my center is at 2. And then my radius have to be within 2 units away from that. So within 2 units of the radius, so 2 plus 2 is 4. And then I can go back 2 as well. 2 minus 2 is 0. So my interval of convergence would be 0 to 4. Meaning if I were to pick a number like 1, 2, or 3 and substitute it into here, so if I were to replace x with 1, for example, I should create some sort of geometric series that converges. If I were to pick x equals 3, it should create an interval, or should create a geometric series that converges, but not 0, not 4, right? Because if x were 4, so let's test that. So if x were 4, so we're going to take that equation, and then I'm going to replace x with 4. So 4 minus 2 is 2, so 2 to the n divided by itself would reduce, and then I would have negative 1 to the power of n. My absolute value of my radius or ratio would be 1, which is not less than 1, and so then this would diverge. Okay, and that is it.